right, good morning, everybody. So today we're going to start into Chapter 3, Section 1. And Chapter 3, Section 1 is a kind of a continuation or maybe even an advancement of what we just got done talking about, which was doing all the factoring and the completing the square and the quadratic formula. All of those sections that we just previously covered were to kind of brush your skills up on your ability to manipulate and solve quadratic equations. Now, we're going to be moving forward with quadratic equations and kind of diving in and discussing a lot more things in detail about them. For instance, how to graph them more specifically, as well as solve and also write a quadratic equation given certain parameters. And so all those prerequisite skills that we just finished going over are going to be used to do now what we're going to start talking about. So you can see this is called quadratic functions and models. Here's a few of the things we're going to be doing. We're going to be analyzing graphs of quadratic functions, writing quadratic functions in vertex form and using the results to sketch the graph of functions. And we will also be finding minimum maximum values of quadratic functions in real life applications. So the graph of a quadratic function. So the first thing we want to look at is to notice the difference between these three equations. This equation right here, as you can see, is called a linear function. And the reason why it's called a linear function is if it were graphed with numbers for the m and the b, which are your slope and your y-intercept, you would get a graph that is a straight line, otherwise known as a linear graph. This second one, f of x equals c, would be a graph of a constant. And a constant graph would be something on the order of like f of x equals 3, right? So that would be just a graph of a straight line. It would be straight horizontal line crossing the y-axis at 3. And so it's called a constant because it doesn't matter what number is inputted into that function, the output will always be 3. The last one you see here is called the squaring function. And that, as you might suspect, has a square in it. And it is going to be graphed. And when you graph it, it does not look like a straight line. And that's going to really be the key difference between a linear and a constant function when you move into higher order functions, such as x squared, x third, x to the fourth. The lines no longer stay straight. They start to get curves. And to be honest, the higher powers you have, the more potential for curves there might be in the graph. And we're going to talk about what causes that as we move forward in the next few sections. This particular graph would look like a U, and that U is called a parabola. Any function, all of these, including the linear, constant, and quadratic, and even higher order, so cubic, quartic, quintic, all the way, fifth degree, sixth degree, seventh degree, they're all called polynomial functions. So polynomial functions is a generic term for any function that we have that we're going to be looking at. Now, this is a definition of a polynomial function. Now, I don't want it to scare you. It does look a little bit intimidating when you begin to kind of look in and see all these different variables. But once you kind of figure out what they actually mean, it's really not so bad. If you look at this a sub n and then a sub n minus 1, and then it goes all the way down to a sub 2, a sub 1, and a sub 0, those are simply the constants. So that would be like having right here 2x to the fourth. Okay, so a sub n would be the 2. Now the x to the n is simply saying it's x to whatever the highest power is first. And so if you look as we move down through here, you start with n, and then the next power is n minus 1, or one number lower. And it continues that trend until you have x squared, then you have x to the first, and then you don't have an x at all. It's just a constant term left, which is the a sub 0. So really all this is saying is that when you have a polynomial function, it's going to be ordered from the highest power of the x down to the lowest. Polynomial functions are classified by degree. And so it says, for instance, a constant function, f of x equals c, which c would just be a number. The degree of that would be 0 because there is no x term. If you had, for instance, f of x equals 2x plus 1, the degree would be 1 because the power of the x is 1, and so on. So if you had an x squared, the degree would be 2. If you had an x cubed, the degree would be 3. And so this just gives you an example or multiple examples of what quadratic functions could look like. The first one that you see here is in standard form. The next one that you see here is what we're going to soon learn that is called vertex form. And as a side note, that is what you would get if you would complete the square the way that I showed you in the previous sections. The next one is not really in standard form. It's just kind of mixed up a little bit. The k of x is in standard form, and then this would be what we would call factored form. If you did FOIL these out like this, you would get something that looks more along the lines of what you see up here. Okay, so the definition of a quadratic function is ax squared plus bx plus c. And it's called a quadratic because the highest power that we will encounter in this type of equation is going to be x squared. Now, this is something that you are probably already familiar with. We have called this standard form. And as I said in a previous video, your book, for whatever reason, calls this general form, which is ax squared plus bx plus c equals 0. So when this function, we get rid of the f of x, but when this thing equals 0, that's going to be called standard form or general form, as your book calls it. And as we said, when you graph a parabola, when you graph a quadratic function, it will give you a parabola. Now, parabolas have some aspects that are important that we understand moving forward as we go to graph them. There's a couple things that we need to talk about. The first thing we need to talk about is what is called the axis of symmetry. And if you look right there, I just highlighted that. And what the axis of symmetry simply is it is a line in the parabola, and it will always go right through the vertex. But it is a line that if you took that parabola and you flipped it, it would be exactly the same. You would not change the graph whatsoever. So that's why it's called an axis of symmetry, because you could spin on that axis and the graph is going to look symmetric no matter which way it's flipped. Okay? Now, the next thing that we need to talk about, and I kind of actually just used the term, but you should already know this, is this point right here. This point right here is called the vertex. And the vertex is either the smallest amount that you'll get or the largest amount that you would get from the graph, depending on whether your graph opens up or down. Now, the one thing to keep in mind is each of these ends of this parabola do have an arrow on them, so they do continue. So for instance, the first one continues up forever, goes up and up and up. Now the second one goes down forever, so there would be no minimum to that, but there would be a maximum, and the maximum happens right there at the vertex. The same idea here. This one goes up forever, so there would be no maximum, but there is a minimum value, and that minimum value happens at the vertex. Now, in Algebra 2, you had a way to find that vertex, and there was a little formula that you had to do that. But we're going to be graphing these slightly different than the way that you did in Algebra 2. The last thing that I want to show you about a parabola is why the parabola opens up or down. And the reason why it opens up or down is completely controlled by this number right here. This a number, so the number that's in front of the x squared term, is what determines if the parabola opens up or down. So you can see I highlighted a, and then over here to the right, you can say that a is less than 0, meaning that a number is negative. If the a number is negative, you will get a parabola that opens down, just like you see me highlighting. Okay? And along the same lines, if this a right here, the number that is in front of the x squared term, is greater than 0, meaning it's positive, then you will get a parabola that opens up. And it's a very easy, quick indicator to look at. Maybe you've gotten a graph and you're like, I'm not sure whether this thing is right. Look at the a of the equation. Is the a positive? If it is your parabola opening up? Same thing. If A is negative, it should be opening down. That's a really quick, easy check that you can do as we continue looking at these and eventually graphing these. So I want to show you when sketching the graph of f of x equals a times x squared, it is helpful to use the graph of y equals x squared as a reference. And I'm going to show you what that means here. So as we're looking at these two graphs right here, you can see there are two graphs that they want us to graph. They want us to graph f of x equals 1/3 of x squared, and then they want us to graph f of x, or excuse me, g of x equals 2x squared. And so what I want you to see is what this number out in front of the x squared, so that's our a number, what it actually does to the parabola. Not only does it control whether the parabola opens up or down, it's going to control whether that parabola gets stretched out vertically or if it gets smushed down vertically. And so you'll see the difference. Now, and this is what you want to think about. If I would take a number and I'd multiply it by 1/3, I'm making that number smaller. So what do you think that's going to do to the parabola? It's going to make the parabola smaller. Now, when you smush it down, if you think of like a piece of gum or something, if you smush a piece of gum down, that gum is going to get wider and flatter. And that's exactly what this parabola is going to do when you have 1/3 x squared. Along the same lines, when there's a 2 in front of there, that 2 is going to take the y values and it's going to stretch it out. And again, you can think of a piece of gum. If you take a piece of gum and you stretch it out, it's going to get longer, but that gum is going to continue to get skinnier and skinnier. And that's exactly what the parabola does. So as we look at the graph here, the easiest graph to start with is going to be the graph of just y equals x squared. And you can see that graph right here in gray. That is the graph of y equals x squared. If I were to make a table for that graph, I'd start at 0, and I could do -1, -2 like this. You would plug that in, you'd get 0, 1, and 4, and then 1 and 4 right here. So you can see you get 0, 0, 1, 1, and then 2, 4 is going to be up here. And then -2, 4 is there, and then -1, 1 is right there. So that graph in gray is the graph of x squared. And this is why it said use that, and we're going to be calling those parent functions. That is the parent function of x squared. Use that x squared graph to then draw or sketch what 1/3 of x squared would look like. So going up here and looking at this first graph, you can see, again, that 1/3 is going to smush that graph down. It's actually going to take every one of these y values and multiply them by 1/3. So you can see I'll do the dots in red here, but the vertex here is still in 0. But now instead of the next point right here being at 1, it's at 1 times 1/3. Which is just 1/3. So you can see it's only 1/3 of the way up to where it should be because it got smushed down by that 1/3. The same is going to hold true for this number 4 up here. Normally it would be at 4, but it's at 1/3 of its height now, which is slightly over 1. So you can see what that 1/3 did. It smushed the graph down and made it wider. Now, the same idea is going to happen with this one. If I would go back, I'm going to draw that table here real quick again. 0, 1, and 2, -1, -2, 0, 1, 4, 1, and 4. So that would be the table of y equals x squared. And then that's what we would get with, again, this is the gray graph that you see right here, okay, that I just highlighted. Now, if you put a 2 out in front of that x squared, now what it's going to do is it's going to multiply every single one of the y values that see over here. All of these y values are going to get multiplied by 2. So now we end up with 8, 2, 0, 2, and 8. And if I were to go graph those, we get 0, 0. The vertex still is at the origin, but now when it's at 1, it's up here at 2. And when it's at 2, it would be way up here. It's going to be way up here at 8, which there's not even enough on the graph to show you that. So it would be roughly up here, maybe even higher. So this would continue way up like this. So as you can see again, because of this 2 out in front of the x squared, the 2 is going to stretch all those y values out and make them 2 times bigger. So it makes the parabola stretched vertically, but skinnier. Okay, so this is just a quick example of what is happening, and I'm going to go over transformations a lot more in depth later. But just to show you, if you look at this parabola right here, you can see the lead coefficient is -1. And so what happens is we start with this parent function x squared, and what it does, that -1 flips the parabola over. Now, the other thing that this part does, that +1 raises the vertex up by 1. So not only did we take this parent function, which is just y equals x squared, you can see I just traced it, we flipped it over, and then we shifted that up by 1. This other one is not going to flip anything over because the lead coefficient is still positive, but it is going to shift it to the left by 2 and then down by 3. Now, again, I'm not too terribly worried about you completely understanding this yet. I'm going to go into this in much more detail. I'm just showing you what information that we can get by simply looking at a quadratic equation. And this quadratic equation is actually in vertex form. And you'll see why that's super useful, because then we can just graph these without having really to make much of a table. And that's kind of where we're going with this. Okay, so you've heard me talk about vertex form. I want to formally give you the definition of what vertex form is. So we have 2 forms of a quadratic equation. We have a form that is f of x equals ax squared plus bx plus c. Okay, that's the first form, and that is called standard form. You learned that last year. The book calls that general form, but they do mean the same thing. Standard form, general form, they are going to be the f of x equals ax squared plus bx plus c. And so now this year, we're going to move into a new form of a quadratic. And one of the things that you need to understand is this is very similar to when you had different forms of linear equations. Linear equations actually have 3 different forms. I'm actually going, we just had a test in my Algebra 1 class for that. And their 3 forms are slope-intercept form, point-slope form, and then the third form is standard. And so I don't know if you even remember, but we did review those at the beginning of the school year whenever we worked on the review packet. So linear equations can take 3 different forms. Quadratic equations, what we're going to study, can have 2 different forms. So the first form of a quadratic is standard, or as your book calls it, general. And the second form here is going to be called vertex form. Now, vertex form is extremely useful with quadratics for a couple of reasons. The first of which is it's very easy to identify where the vertex is. The other reason why vertex form is really useful is it is very easy to solve a quadratic equation that is already in vertex form. A quadratic equation that is in vertex form does not need to be factored or does not need to have the quadratic formula used. You can actually just solve it based on the equation once it's in vertex form. So here's what you need to know about vertex form. This first number a right here, that a controls 2 things. It controls whether the parabola opens up or down, as I showed you. If a is positive, it opens up. If it's negative, it opens down. The second thing that a controls is how stretched out and skinny or how smushed down and wide the parabola is going to be. Now, the reason why this is called vertex form is because of this and this number right here. Now, these will be numbers, and as an example, I'll write an equation. F of x equals 2x minus 4 squared plus 6. So there would be a quadratic equation in vertex form. And this is the really important one. The h and the k are where the vertex of the parabola exists. Okay, so in this particular case that I wrote under here, the vertex would be 4, and it's not -4 because the formula itself has the minus in it. So it's just 4 and then 6. 4, 6. Now, remember, if you remember previously in last year or even at the beginning of this year, to find the vertex when something was in standard form, you had to use the formula negative b over 2a. And that just gave you the x value. And once you got a value for that, you had to plug it back in to this to get the y value. Now, if it's in vertex form, we can just identify what the vertex is.